Hi, my name's Lena, and recently I moved from well-known hotspot Brisbane, Australia, to study engineering at Northeastern Boston. And through these last few months, I've experienced what not many Australians have: an actual cold winter. I've experienced the parts that are good, the parts that are bad, and the parts that are just downright freezing. So that's why I've taken upon myself to prepare any incoming engineering minded Aussies through all I've learnt, with my Engineer's Guide to Surviving the Cold, Australia versus Boston edition.
So, you're ready to make the move. You're ready to swap volleys for sperries, ibis for geese, and this for this. But most of all, the most important change is going to be the weather. More importantly, the temperature. Now, I know what you're going to say. Selena, it gets cold in Australia. Last winter I nearly spent the whole time in my tracky dacks. But I'll tell you, if you go up to anyone in Boston and tell them that the average winter temperature is about 22 to 10 degrees, well, first, they may be very confused because they use their own temperature scale. But once you explain that that's about 70 to 50 degrees Fahrenheit, they may laugh in your face. So that's where I come in, my fellow cold-seeking Australians. I'm going to explain to you just how heat transfer can help you not look like a drongo and survive this Boston winter. So I'm going to tell you right now, mate, that flannel's not going to cut it. And I know what you're thinking. Selena, why don't we just wear warm clothing or layer up until we feel comfortable? And to that I say, engineers have never made anything simple before, and I'm not about to start now. Now, here in Boston, we have a few things working against us. Firstly, it being one of the windiest cities in the USA, and secondly, it being near the coast. But the latter affecting us has a little bit more to do with thermodynamics, and I am not opening that can of worms today. So, back to that wind. Wind is an example of one of our three mediums of heat transfer. Our first one being convection. As warm air heated by the sun and Earth's surface rises, cold air whooshes in to take its place, causing wind. That cycle repeats itself as that cold air flows over the surface to then get heated again. As that cold wind brushes past you, it may take away some of your body heat and cool the air around you. So let's have a look at our board to take a closer look at what exactly is going on here.
Convective heat transfer is energy transport due to bulk fluid motion. Convective heat transfer through gases and liquids form a solid boundary layer resulting from the fluid motion along the surface. With the example of wind, the temperature of the surface is greater than the temperature of the surrounds. Newton determined that the heat flux is proportional to the fluid-solid temperature difference Ts minus Tf, which is also known as our temperature gradient. Additionally, this is the driving force behind the heat transfer. Newton's law denotes that Q double prime equals H outside of T of the surface minus T of the fluid. Q double prime denotes our heat flux, H is our constant of proportionality, and Ts minus Tf is obviously our temperature gradient. Now, our constant of proportionality, H, is also known as our heat transfer coefficient, with the units watts per meters cubed per Kelvin. The heat transfer coefficient depends on the type of fluid and the fluid velocity that's occurring within the system. So H can actually vary significantly depending on the description of your system. As we know, our Q double prime equals our heat flux, which actually just equals our heat transfer rate divided by area. Through this, we know that our actual heat transfer is heavily reliant on the surface area of which the heat transfer is occurring.
So Vinny, with that knowledge of convection, what do you reckon we should do?
I don't know, get out of the wind.
Yeah, or we can reduce the surface area of our skin exposed to the wind by layering up. By introducing layers to protect our body heat, we're introducing our second medium of heat transfer, conduction.
Conduction is the process by which heat is directly transmitted through a substance of certain properties and of certain specifications. This is normally when there's a difference of temperature between the two adjoining regions without movement of the material. Fourier determined that the heat flux is proportional to the temperature gradient dt over dx, which brings us to Fourier's law, where Q double prime equals negative k outside of dt over dx. Where Q double prime is again our heat flux, k is our constant of proportionality, dx is the thickness of our wall, and dt is our temperature gradient. Our constant of proportionality here is K, which is our thermal conductivity. It has the units of watts per meter per Kelvin. Thermal conductivity depends entirely on the material, so you could essentially have two walls of the same dimensions with heat flowing through on one side at the same rate, but one has a high K value and one has a low K value. You'll notice that the wall with the higher K value will have a significantly smaller temperature gradient than that of the one with the low K value. This is as a high thermal conductivity allows for heat to travel more freely through the wall, thus resulting in a higher T2 value than that of a lesser conductive wall. So, what does that mean for us here in Boston? That means that we should ensure that all of our clothing is of a quality that retains our heat, and also increasing the thickness of our protective layer by layering up.
Why do we need to do any of this? Why doesn't the sun work here like it does in Australia?
Well, Vinny, there's actually a pretty simple explanation for that, which brings us to our third and final medium of heat transfer, radiation.
So, what is radiation? Radiation is the emission of energy as electromagnetic waves or subatomic particles from a high energy surface or volume. Now, as an example, the sun is a big sphere of hot plasma made up mostly of hydrogen and helium, emitting a magnetic field. So, it's definitely got a lot of energy to go around. Additionally, radiation does not need a heat transfer medium, which explains how we receive the sun's heat here on Earth, even through the vacuum of space. We quantify this through Stefan-Boltzmann's law. It explains that the heat flux radiated from a body is equal to the constant of proportionality, or the Stefan-Boltzmann constant, times by the temperature of the emitting body to the fourth power minus the temperature of the cold surrounds, also to the power of 4, making our temperature gradient. Our Boltzmann's constant, which is our constant of proportionality, is always constant no matter what the system is, and it's equal to 1.38 times by 10 to the negative 23, with the units of meters squared, kilograms per second squared per Kelvin. But there's one thing wrong with this version of the law. It assumes that we're dealing with a black body. A black body is a body that absorbs all radiation that falls on its surface, therefore having an emissivity of 1. They actually don't exist in nature, therefore emissivity is one more important variable that we need to take account for. Emissivity is defined as the ratio of the energy radiated from a material's surface to that radiated from a black body under the same conditions. Therefore, it's a dimensionless number between 0 and 1, and this is how we correct for imperfect emitters. For example, the sun has an emissivity of 0.986, making it a very good emitter. Now, as the heat radiates out from the sun, it expands over a greater surface area and experiences a few losses, which is why by the time these waves reach Earth, we are heated up to a nice and comfortable temperature range. But then that leaves one more question.
So why doesn't Boston get as much radiation as Australia? Well, that brings us to our final Boston attribute that's working against us, our solar angle.
Oh, what?
Our solar angle, which is produced by the tilt of the Earth's axis.
The Earth's axis is tilted slightly at an angle of 23.5 degrees. This tilt
Vinny!
Alright, let's slow this down and take it back to the blackboard.
Now, the Earth's axis is not exactly at a right angle with the sun. It's tilted slightly at an angle of 23.5 degrees. Because of this tilt, it not only affects the positioning of countries in the relation to the sun, but also the amount of daylight the country will receive. However, a country's position relative to the sun mostly is what will determine how much radiation it will receive. The angle of incoming solar radiation influences seasonal temperatures of locations at different latitudes. When the incoming solar radiation strikes at the Earth's equator, it's much more direct, hitting at almost 0 degrees. Therefore, the radiation is concentrated over a smaller surface. However, at higher latitudes, the angle of solar radiation is larger, causing the energy to be spread out over a larger area of the surface and resulting in cooler temperatures. This relationship is explained through the Lambert cosine law. It explains that heat emissions received at angle B is equal to heat emissions received at angle 0 times by the cosine of the angle of incoming solar radiation. So whose solar angle do we think is higher? Boston or Australia? You guessed it, it's Boston. With significantly chillier temperatures and a lot more snow, this is quite unsurprising. On average, in the winter, Boston's solar angle is about 66 degrees, as compared to Australia's 52. This results in about 40.67% of heat emitted from the sun reaching Boston and 61.57% reaching Australia, which is significantly larger. It's worth noting that in the summer, Australia's solar angle is on an average of about 4 degrees. This results in about 99.75% of solar emissions received at an angle of 0 received in Brisbane, Australia. No wonder we're no good with the cold. So I think the final verdict here is, we better rug up until spring.
Now, Vinny, through heat transfer, do you reckon you're going to survive the Boston winter?
I think I'll be good from now on.
And I'm happy with that. Let's do that.
I've learned so much today, Z. Thank you for convection and stuff.
Zerlina, why don't you Alright. So, back to that wind. Wind is a perfect example of one of our first mediums of heat transfer conducted.